All right, so we're going to talk a little bit about volume change, stress deformation for unsaturated soils. And again, I'll continue with my theories of dividing the stress state variables into two different, combinations, right? Great discussion during the break on how you just, if you combine the normal stress with the pore water pressure, you're working still with an effective stress. And, but, at the end of the day, we obtain the same results, actually, if we use those surface and those two kind of three-dimensional plots. And we're going to see that on the volume change right now. So what I have here are constitutive models for the stress deformation of unsaturated soils. Again, I wanna start from, again, this is the models that we have been using, but that doesn't mean that there are different models available as well that are working. And the compressibility of unsaturated soil. So how do you translate this one into the geotechnical engineering practical? So again, this one I wish we can bring it up on the first thing here. There are many different stress strain models for unsaturated soils, okay? And all of them constitutive in nation, but some of them are just, giving different assumptions. One of them was for soil is pure elastic. Some of them are pure elastoplastic models. And then you just, go into the elastic model. You can use linear models, non-linear models, or, all of that. And in the elastoplastic models, you can also do a different set of models in here. And basically, this one is nothing but what is a model, like, is something how you're going to be estimating or representing the stress strain behavior, right? So you can do a model that, is just, creeps away like that, or just start hardening models, or you just, a relaxation, or you just kind of unload it. So it's not how you represent that. And it has to be whether you include only elastic side of it, or you include the elastic plastic behavior of the soil, right? Some of them are going to require loading and unloading. So how much of this strain is reversible, how much of this strain is not reversible, and so forth. So there are many models available for doing that. But again, Fredlan and the colleagues, which is the theories that I manage, they basically use a nonlinear elastic, kind of incremental elastic model, right? It's an incremental elastic model. Suction with hardening plastic constitutive models for unsaturated soils. But we're right. If we keep going with the matrix suction or start increasing the matrix suction, the soil will lose all the stress parameters because you have no more water, right? So all of them eventually will just go to a point that it's just going to go like that. And obviously hardening behavior will not be anymore. But for the range of suction that we're working in our soils, probably unless we are in the moon or in the, I don't know what desert, then we're not going to have that falling down, right? So elastic models are modified incrementally. That's what they do. And the modulus are based on the void ratio, state surfaces. Basically as first defined by Matthias and Radhakrishna in the 1960s. We got Poisson's ratio is typically estimated. You can, certainly measure that if you have the means of doing that. And in general, there are path dependencies not incorporated into those models. Okay. The more Coulomb failure, surface expands, exhibits hardening with increasing the soil suction. Via an increase in apparent cohesion, like I just showed you before, we can include that matrix suction into that. And also exhibit softening with decreased suction. So volume change can be expressed in terms of deformations of phases of the soil. And again, can use different phases. The two sets of deformation stress variables that are required are the deformation of the state variables associated with the soil structure, and those deformation of the state variables associated with the water phase, the two of them. So if you consider an element of soil that deforms and it applies different stresses, you consider like we did it before, the contracting the skin as part of the solids. you can say that the change volume with respect to the initial volume is going to be the change in volume of water plus the change in volume of air if you consider the solids to be in compression. Okay. So the overall volume mass constitutive model, and we're using again linear elastic incremental model, right? So segments on that and just to get the nonlinear behavior, but it's just basically multi-segment. We need a deformation state variables with the appropriate stress state. Remember that you're going to need the stress and the deformation, right? And these are the questions that we do have for linear elastic in the 3 dimensions, in which you include the modulus in here, stress, the modulus, the stress over strain, and include to get into the 2-dimensional, 2-dimensional, you're going to need the Poisson's ratio right there, all right? And the total volume strain is going to be the summation, again, superposition of the strains at the 3 directions. So when you have a saturated and an isotropic, okay, linear elastic solid structure, the stress-strain constitutive relationships are pretty much the Hooke's law, right? That part of it. And the volumetric strain is the sum again of the normal strains right there. So the volume mass constitutive models, when we talk about normal strains, the normal strains in here, for unsaturated, so these ones were, for saturated isotropic conditions, right? For saturated isotropic conditions. When you get into the unsaturated isotropic conditions, basically you're going to need to add the extra component, okay? I divided the normal stress in here, the water, I put it with the total stress, so I don't use effective stress, and I put on this side the matrix suction, right? The matrix suction contribution to that, which is going to have their own modulus. In this case, going to be the modulus of elasticity for the solid structure with respect to change in matrix suction, okay? So all the volumetric strain is going to be the sum of the normal strains, the same way as we did before, or we have done before for saturated salts, we're going to be doing it here again for unsaturated salts. But now we're going to have the extra contribution of the strain due to the change in suction, separated from the change in the normal stress, okay? So when you solve that, the shear deformations are going to be the same, the ones in the faces of the element that we consider going to be shear strains, and we're going to have normal strains in here. That's going to be, this one is going to be your 3-dimensional tensors for, or the shear strength, the normal shear strength that is going to be the deformation tensor, okay? So the volumetric strain change is what we want, the change when the change in the stresses will happen, right? So you're going to need is the volumetric strain change is equal to the volume of the voice change that you're going to have divided by the initial volume, all right? Again, it's a summation, it's superposition of the 3 dimensions plot. This one is the question that you just saw before for one condition, and then you solve for the change in the volume of voids when when you use that equation. So again, we got divided the 2 stresses in here. So that's the same equation. The constitutive equation for the water phase is going to be, now you're going to have the same equation, but now it's going to have for the water phase, right? And in here it's going to be the modulus for the water volumetric modulus that is associated with the change in the mean net normal stress, and this one is the water volumetric modulus associated with the change in suction, right? For the air phase, usually it is computed as the difference between the overall structure strains minus the water volume changes, okay? So, and now you do have the whole change in the voids by the change in the volume of water plus the change in the volume of air. So that's how we get those 2 parts. One with this equation, the other one, the difference between the one that you saw before and this one, right? So in that case, again, we divide it and we use a three-dimensional plot analysis to figure out the constitutive surface, right? The slopes are given by the equation that we saw before, the change in strains. So if you check in here, the soil structure is going to be the volumetric strain as a function of suction, and the volumetric strain as a function of net normal stress, right? You're going to have the two stress and state variables in here, and for the water, you're going to have the change in volume of water with respect to the initial volume of water as a function of suction and as a function of net normal stress. And you actually, what you have is a surface, right? As a surface, if you consider them in that way. If you do an arithmetic scale, it's going to look like that. And basically, for that, you're going to have a different, relationships that instead of, being that way you're going to have them on this nomenclature, but it's the same thing. It's just only on the arithmetic scale. One of them for the soil structure, and the other one is for the water content, constitutive surface, or in the arithmetic scale. All right. So this is how we estimate the volumetric, the changes, the change in volume, and it's just a linear elastic theory, right? And again, this is just one of the models, doesn't mean that there are no more models. There are many, many more models that are available, as I showed at the beginning, and all of them have a different way to estimate. So how we apply this one to our geotechnical engineering problem, right? For saturated salts, you are very familiar with that equation. This is your consolidation equation, right? In the arithmetic form with the change in void ratio as a function of the change in effective stress, because in the saturated state you got the compressibility right there, right? The C sub C, if you use the log scale. But this is the consolidation equation that you should all know about it, right? And be familiar with that. When you have unsaturated salts, again, you divide the two into the normal stress and the suction value here. And now you're going to have two compressibilities, right? The one is the coefficient of compressibility with respect to the change in net normal stress, A sub T, and the other one is sub AM, which is going to be the coefficient of compressibility with respect to the change in matrix suction. So that was the plot that Professor Ballard was doing here. That was the change in void ratio versus the stress state variable. They're going to be looking like that. They're going to be looking like that, okay? One goes independent of the other one, right? Independent of the other one. Same thing for the water volume change. You're going to have the coefficients of volumetric water change. Okay, we're going to go for the next one. And this one is for the water content. Again, for the saturated soil, you're going to have the change in water content with respect to the net normal stress, right? And you're going to have here a function on coefficient of water content change, right? With respect to the net normal. For unsaturated, you're going to have two. You're going to have this one with respect to the net normal stress, but this one with respect to suction, right? The B sub T and B sub N, the two of them are coefficient, and they're going to be behaving like that, separate to each other. When you look at the surface, it's going to be looking like that, right? So those are the constitutive surface for the unsaturated soils. We're using just the expressions that we use, right? We just don't using the one that we use for constitutive model. But those are the terms that you become now more familiar with. Now, if we get into the compression index, when we get into the compression index, we use the log scales in here. Now remember so which one is the one that you'll be very familiar with is the change in void ratio versus the change in stress, right? The change in stress. And this one is a total stress change, which is you're going to have a constant in here equal to C sub T. The 0.43 is the change between log and arithmetic in here. There is another one in here, which is C sub N, which is the change in void ratio with respect to suction. Okay? The other one in here is going to be the change in water content. Okay, now for this constitutive this one, okay? When the soil is saturated, the poured pressure is equal to your forward pressure, right? So this one is like your effective stress, right? That's your effective stress. That's the consolidation curve that you've seen always, right? So what you got in here is this guy, right? Is that guy. And that's your, becomes when the suction is zero, just when the suction is zero, this one becomes your C sub C, right? Now, if you get into the water contents, this is the water contents, and this is the water content change with respect to suction. And you got this slope in here, and this is the water change with respect to net normal stress, all right? The surface will go, they don't go parallel to each other, this one might be much lower than the other one. But do you recognize this relationship? What is this relationship? The change in suction with respect to water content. That's your saltwater characteristic curve, right? That's your saltwater. So the extreme on that one, okay? If you just do a saltwater characteristic curve with no external load applied to it, that's your saltwater characteristic curve. Okay? So this is the corner that you have learned these 4 days, and this is the corner you have learned during your consolidation analysis, right? So in that way, you do have all the compressibility due to a combination of the effective the stresses in that way, and you can represent that one in a constitutive surface. There are limitations and complications, like we were discussing during the break in here, obviously. The loading part is different than the unloading part. So we're going to need a constitutive surface for the loading, right? And another one because we got a different unloading value. Instead of being the C sub S, it's going to be the C sub S, right? And also because we do have hysteresis in the saltwater characteristic curve. And that fact means that, we're going to have a slope or a relationship for a drain curve and another one for the wetting curve, right? But knowing that, it's like going back and forth for whatever we need to go, right? It gets more complicated. But the theory applies whether you're loading or unloading, or the theory applies whether you're drying or you are wetting in here, as long as you use the right coefficient, right? The right coefficient in there. So, question for you, and I already gave you the answer. If you put this one into a log scale, right, you're going to look like this. So can you identify the consolidation curve for saturated conditions in here? Is this one, which I call 1, or this one, which I call 2, or with respect to water content, which I call 3, and this one, which I call 4. Which one are the consolidation curve for saturated conditions? That's going to be 1, right? That's going to be 1. And that's the one that you... And what's going to be the saltwater characteristic curve for zero net normal stress? That's going to be 4, right? Okay. So this is important that you understand how we expand the same theory that we've been using before. Okay. Any question with that? Now I'm catching up with the time, right? Yes, you mind, sure?
Actually, we are having like water is incompressible, and we use it in the conventional compressibility theory. When we are having two phases, water and air, so air is compressible. How do we incorporate that?
The volume change to the compressibility of the
air, yeah.
Compressibility of the air. Well, again, it is included because the change in volume that you're going to have is here, the volumetric change in volume is going to be a function of the change in volume of the water, okay? Which you're right, this is the water is much more incompressible, right? And this one is the change in the voids of the air. So they're going to be in here. We don't have a constitutive relationship applied directly to that, but if you come back to the volumetric change for the total, soil, right? The total. And you subtract from this one the one for the water, which is this one. Then you get the compressibility of the air. Once you get the compressibility of the air, then when you apply that, then you use that one in here plus this one in order to figure out the change in the water, right? So that's how that works. Any other questions on that?
Ma'am, can you explain this EW and HW, that water volumetric modulus associated?
So when you talk about linear elastic analysis, right? Linear elasticity or Hooke's law, right? So you talk about a modulus being equal to what? To the stress divided by the strain, right? So we're solving in here for the strain, right? Which is going to be equal to your stress, whatever it is, divided by the modulus, right? So if we're using the whole mass when it includes the air, the water, right? The whole mass of the voids that are going to be, changing in volume, we're going to be using the elastic modulus. We always use the elastic modulus for that, right? But we use only for the liquid phase, the modulo of the water associated, all right, with this stress, it is associated with the normal stress. We call them EW, which is the modulus of the water, right? Depending on that one. So the modulus is not going to be your elastic modulus. Now it's going to be a modulus of the water modulus that is associated with that change. And in here, the Henry's guy, which is the water volumetric modulus associated with the change in the suction. It's another modulus. You see what it is? So there are 4 different modules that you're going to need probably. There's 4 different material properties that you need. Okay? And those are available. Okay? What do you expect of that? But actually, this one is the one that you just measured. If you just charge some water, right? That's very incompressible, right? So the modulus is very high. That's what Himanshu's, okay? When you get air, it's going to be much lower, right? It's going to be very. And when you have the change in water content, also you're going to have another module.
Yeah, ma'am, adding to that question only, regarding that HW, that is the water volumetric modulus, how to determine it? Is it experimental determined or?
Henry's law.
Henry's law.
Henry's law.
It is, there is data available for that. There is data available, but you can actually determine if you want it experimentally, but it's data available for that when you just, people have done the water and, have been associated with different suction changes or net normal stress change. But this is Henry's law. So the values are available. You can see the values all over the place on tables. So that's what, I think we'll use on that. I can bring that over, I could find those, but yeah.
Excuse me.
Yes.
Just was that does this model capture collapsible as well as expansive soil?
No, that's what we're talking about in here. Well, you're going to see a model that I'm going to bring in here tomorrow for expansive soils that will do that, will capture that, right? But it's also divides the 2 stress state variables in here. Okay, so let's check this surface, right? The thing is, this one is only for linear elastic theories, right? This is for linear elastic theories. So what happens is, if you do have, let's say you got a soil that you're going to be decreasing your suction, right? Okay, so you are in a place in here, right here, okay? And basically, or just 0 volumetrics, and then you're going to be decreasing your suction. which is putting water into the soil, right? So if the expansive soil behave the same as your, these kind of soils, they're compressible soils, then they will follow this line as well, right? And they will just go and compressibility go like that, and you're going to see what is the change in volume due to the expansivity of that. All right. Now, collapsibility. Okay, so what happens if at this point you decided you put water in there and then you decided to load it? Okay, so that's what I'm arguing with your professor, that I think this works with no problem, because you just go ahead and just get the point. The problem is you need to really be careful with this guy, right? Because for expansive soils, the value is different. Now, when you get in here and then you decided to load the soil, okay, and now you're putting soil in this one. Now you are in one of these surfaces, and now you decided, and the soil can start going down, down, and there is even a point when you can get collapsibility due to that. Okay, so if you follow the same surface, and I think this one is not the one that I like to follow. I like this small one in here better, but it's the same thing in here, right? Change in matrix suction, you just solid structure in here. So if you have no volume change, you increase your suction value. So you can go from this point, to this point. You got this value here, and then in this one you decided to increase, and then you just follow this guy in here until even lower. Okay, you ended up in a point on this. So now, whether the linear elastic models, okay, that we use, very simple. You see the question is just a linear elastic model. You can use just, you're using, or we are using only one modulus, right? Where is it? What is in just one model? Right. What? Okay. What is in just one values for those? That's what I'm saying. Okay. Because we consider this to be elastic in a certain range of values. And then we use another elastic for another set of values. Now you can do it as non-linear as you want, right? Depending on the values that you got. But you need to be careful with what we're using here. It's using with linear elasticity. Okay. But yeah, certainly out of a surface like that, you can do any combination of loads conditions, and you can have collapse in an expansive surface. Okay. Good questions in here. Any other questions? All right. So how is our schedule going on in here? So we have another hour, right? After lunch. What again? 22 minutes. We got 22 minutes, and then we'll come back for the last hour, right? So what I'm going to do, so we can go a little bit slower in the next topic, okay? I'm going to start right now. Is that okay? So if we finish before, but I'm very sure we're going to get the hour in here, right? So we're going to continue here for another 20 minutes. We'll finish, but we're going to go for the next, the application for that. All right, so how we do that? There we go. There we go. Thank you. Yeah, I tried always to reduce everything as much as I can because of the time, right? So this one was short. All right. So, and again, I'm going to jump in here into the practical side of our profession, right? And basically, as you saw yesterday, the way that volume change is predicted for or included into the payment design analysis. It's a very empirical way of doing that, right? You get PI passing 200, infiltration or rainfall or something, and then you put them in this one, you add some roughness to the road due to that, and then the roughness will add, will just, you design for that roughness cap value, and that's how you do it. Well, we decided that, we don't want to be, if they don't want to run, by the payment engineering, right? Payment engineering designers don't want to run final element analysis and use the constitutive surface in here when we can go up and down, back and forth on time and space, then we could run some closed form solution for them, but based on mechanistic principles, based on the two stress state values, right? The net normal stress and the suction values. And mostly on the suction values, because this is actually will change. When you have a road, if you have a road, the road has some overburden pressure on top, right? Has the granular material, the asphalt layers, and that thing doesn't change much during the year of the payment. Add a little bit of, surface layer or something, but actually the net normal stress, the static load applied to a payment structure, is usually kept constant, right? It's kept constant, correct? So any changes in volume change due to the expansive soils, right? The expansive soils will be due to the changes in suction, the stress of the suction, okay? Now, if you go down with overburden, and that's, we're gonna see that, and I'm just putting everything in a little summary at the beginning. If you go down in an overburden, the overburden is going to be more and more and more as you go down, right? And that overburden is like adding load to your soil elements. Therefore, the elements of soil at a greater depth can collapse, right? Can collapse with no problem because you have a big load on top of it, all right? So this is the principle we're going to be using to estimate a much better value for payment analysis and design based on suction, right? So how we predict volume change for expansive soils under covered areas, and we did that one for payments. Again, I brought my nice pictures of cracks that appear because of the changes in the expansive soils. So, but and you're very familiar with the problems we face with the changes in volume due to expansive soils and the damage in roads. Okay, so we need the ability to continuous monitor volume, or to estimate a continuous volume change is important. And well, because we do have this one as a way of weather conditions. And again, I always, we're doing this graph for many, many times, but again, payment design and analysis is the changes in distresses like fatigue cracking, and too close, thermal cracking, IRI, rotting, and so forth. And it's the change in time until it fails, right? Until it fails. So if we are able to do that, instead of putting the IRI one fixed value that is going to be increasing the IRI, this is the IRI change, let's say due to the, to rotting, plus cracking, thermal cracking, plus fatigue cracking, and then if you add a little bit due to the expansive soil, it's going to be a constant, right? Because it's PI passing 200, and the rainfall, probably the rainfall is going to add a little bit more, probably on a jumping in here, right? In this case, we want to figure out how to estimate that volume change with time. So we do a better predictor in that particular parameter that we are using on the IRI for payment analysis. So something that allows for the prediction of the potential cumulative payment roughness due to the volume change was desired, and we got two great students working on this project about 3-4 years ago, Austin Olays and Mohamed Moussaoui. Here. So basically, the general approach that we did was incorporating a suction-based framework for estimating the volume change of a shrink and swell, goes back and forth, due to the time varying effects, right? Time varying effects. So what happened with the climate and how this affects and how I can do that? How can I study that? So we used to establish a deterministic approach for long-term volume change prediction. What is a deterministic approach? Well, deterministic approach is when you get a value, just one value, right? And you have no associated variability with that particular value, okay? That was, and again, we can do that one for probably forensic engineering, not for prediction, all right? So we did it for forensic engineering. Forensic is when you have to go to the field and figure out what's going on, why is damage, okay? Is that a cause of expansive soil? Now we need to figure out, right, how much that will expand. Litton, Bob Litton from Texas A&M, Albany, Bluth, great group also of researchers that have done this. So we use the same kind of framework that they use for post-tension slabs. Post-tension slabs are the one that we use very common when we have expansive soils for residential construction foundations, okay? And basically, these are, way more ahead of design on expansive soil than the pavement people, okay? But we updated that and we considered all the shortcomings that we got on this prediction, and we said, okay, we're gonna do a little better job on trying to figure out this deterministic approach that they have, okay? So we updated with consideration of short-term conditions. When you have a deterministic approach is when somebody asks you, okay, in the field, I do have this expansive soil, and I want you to take this laboratory testing and give me a value for the expansivity of the soil. You just give them a value, right? And usually you gave them a maximum value. That's it. Well, does that mean that's the one that we should be using for design? Perhaps not, if you have these changes with time problem here. Okay. So we also updated, including an stochastic perturbation on that, because we said, okay, and every problem should be adding a stochastic analysis to it. Why? Because we're dealing with soil properties that vary absolutely tremendously from one place to another one. We're dealing with climatic conditions that if you use 1 year, the next year is gonna be changing dramatically as well the next year. So you can have some patterns, but you have some variability associated not only with the soil properties, but also with the climatic conditions. And not only that, we also have a spatial variability. Okay? It's not the same volume change that you're gonna get at the side of the road by the shoulder than in the middle of the road, okay? It's not the same. So there's gonna be some variability associated in there that we need to take into account. So, and the other commission thing that we had to do was that should be implementable by practical engineers. In other words, they didn't want a final element analysis model, all right? They didn't want, I know we geotechnical engineers do it, we have no problem. Pavement engineers have trouble running something more than 5 minutes, okay? So they have problems. So he said, okay, we do have a guide. We got the IRI in there. We don't want to deviate much about what we're doing business in here, but we want a factor in there for the site factor to be a much better or based on mechanistic analysis, okay? So that's why we went through this route instead of doing, modeling. So we implement a mechanistic stochastic approach to do that. What do I mean by mechanistic and stochastic? Well, mechanistic means, it's based on proper theory, right? Proper theory and stress state variables. And the second one is stochastic. So I'm going to give them variability associated with that. That at the end of the day is the one that is going to give me the rawness of the payment because of that variability. So this is the framework. We're not going to be working on that, but I'm going to be working on batches, right? On those. So, but I gave you the whole kind of a step-by-step procedure that we did, and all of these, steps obviously have a lot of work involved on that. That I even didn't bring in here all that, but we got 16, 17 steps in there for you to read. But then I'm going to go through that into batches, right? So what did we do? The first thing was, okay, we need climatic boundary conditions, right? You're going to be doing that, so we're going to need climatic boundary conditions, and we use the same Thornton moisture index that you did. Now you're very familiar with that guy, and we said, okay, we can modify this one from being an annual index or one number for that modified into a more seasonal variation, right? So we start working into monthly categories for that. So collected the data from a satellite data like MERA, for example, or NOAA. NOAA also has a lot of data there. I don't know if the climatic data is available for free in India. Is it great? Many countries you have to pay a lot for 1 year of information, unfortunately. Okay, so you got that advantage that you can get years of good data, and we collected that data. We extracted data from the nearest weather station that we needed for a particular project or road, right? And we included year, months, monthly precipitation, and average temperature. And why we went for monthly and not for daily or hourly? Well, because expansive soil takes time, right, to respond to that. So it will be very naive to think that you can predict everything that's going on every single day, okay? So we just go for seasonal. Actually, seasonal might have been working okay, right? But we did monthly. And we said, okay, we're going to have monthly variation in here, and therefore we're going to collect monthly precipitation and average temperature. Okay. There is an open access Thornton moisture index GIS map for the United States, which basically you just get, and I can give you it's in Google. You can just go over there and click in any place, and it will bring the weather station when they calculated an annual value based on 2 years, like in 2006 and 2025 or something like that, or 2020, I guess. So to compare on that one, and basically those are numbers that you use as a basis for analysis. But we collected from any place, but this place particularly, we got latitude, longitude, elevation for about 10,000 weather stations, information on that, with annual precipitation, annual potential evaporation, 30 years TMI values as well. Okay. So this one is how you calculated that TMI that you used yesterday, right? The TMI that you used yesterday. And again, the Thornton moisture index is very old, 1948 when it was postulated. And basically that was part of the development of a classification of a system for climate condition based on a moisture index, right? And these are the equations that Thornton used for that. Remember that precipitation is easy to get, right? You got precipitation data from any weather station, but potential evaporation, okay, is difficult to get. It's difficult to get, okay? So the potential evaporation, there are equations that were postulated that are a function of the length of the day and an n value, which is the number of days in the month, and the temperature in here, and this one is the mean monthly temperature, okay? And this one can be used for a daily value for potential evaporation, all right? A lot of people, I think if you go for weather station data and you just click, give me the potential evaporation for that site, it might be using an equation like this or similar to calculate that value, okay? So now, We got also for monthly, we can just use the same equation for monthly data. And we can also do it for an annual index, making the summation of those potential evaporations for the monthly data, okay? So this is how you do a TMI annual, monthly, or daily, right? We just TMI no, but at least potential evaporation. This value here, the A sub T value, is basically a parameter that is a function of the annual heat index, function of temperature. The annual heat index is a function of temperature, and again, is an empirical parameter that this researcher Thorway collected for every place in the United States, and this has been going all the world. You can Google Thorway moisture index for this place, and it's going to show it. But there are also some other countries that use a different moisture index, right? But it's a measure. Again, it's a measure of the infiltration, the balance between the infiltration and the actual and the potential actual evaporation. Okay, so how we use this data? Okay, we can use it in two different ways. One, we can use historic climatic data. Data that we do have is historic, right? We don't know what's going to happen tomorrow, right? But we have historic data to figure out probably tomorrow the soil suction profiles. And this one is important because when you have, again, forensic studies, you're going to have those when you're going to be called and said, okay, I need to figure out what's going on in this road. Why is that, right? And you're going to make analysis of what happened in that period of time that you have. So we collected average temperature for the month, precipitation, and we calculated a Thorway moisture index, right? Thorway moisture index. How we calculated it, I'm just bringing it here probably, again, this is that index in there, the Thorway moisture index. This one is an equation that we got out of basically what he published. He get all this equation and he put a map. So we went to that map and we figured out what he did and everything, and we came up with a much simpler equation in here out of the map when this is the precipitation. This one is back in 2001. And this one is the potential evapotranspiration. They were using data from agricultural people, right? So they do have also the benefit of plants and stuff like that. But we modified this one and we just use the Thorway moisture index with this one, in which we got the potential evapotranspiration in here, calculated with this guy, not with the one that he gave. Okay, and what we did again, like I've been telling you these days, is that instead of having one value, we just did it an annual index, which is an annual index, but we just did it monthly by monthly. We drop January, we take January. We drop February, we take the next one, and so forth. So we run it like that, and we were able to get kind of, more seasonal variation of the Thorway moisture index. Okay. Again, this is a tendency of the environment to get to that value of Thorway moisture index. Okay, it's a tendency because obviously, everything, if you get more rain, it start going up. If you get more evaporation, it start going down. So this is very empirical. Or you can use it for new and rehabilitated pavement design. In that case, you're going to need to forecast the weather, right? You don't have it. You need to forecast it. In the design guide procedures that we got in the United States, that AASHTO, where what they did is they didn't have any forecast model in there. What they did is they used the past 15 years of information from weather station, and they repeated 15, 15 plus 15 and 15. Okay? Whether it's good or not, this government, they don't believe in climate change. I do believe in climate change. All right, so this is the way they're doing. They're having some weather station information in there available. Okay. Obviously, in that case, we do have information from the past 20, 30 years, more. And you can have average values for temperature for every month, average precipitation, and also you're going to have the variability associated with those 20 or 30 years, right? So now you have the opportunity to do a stochastic analysis. And the same thing, you have TMI, and depending on the number of years you have, you're going to have some variability associated with that running TMI. All right. So I'm going to finish the third one, moisture index, and then we're going to go for the break, okay? All right, so again, this is how we calculated that. We used that equation, and we found this one is for a weather station near Paris, Texas. And, this is the kind of data that you're going to get for any weather station that you get. It's very easy to program. That's not a problem at all. Those equations are easy to get and program. All right, I guess that's what it is. After that, we wanted to get the environmental conditions predicted that way related to the suction of the soil that you're going to get at that particular location, right? So that's the second step that you did on your program, on the project yesterday, right? And basically, we're going to continue with this, how we determine that suction envelopes for the changes in water content or, on environmental conditions, and all the way to the depth of equilibrium value. And we use that one to estimate the moisture content variation. Any questions on the thermal moisture index? All right. The questions are there, pretty simple. Again, if you need to program them or something, it's very easy in a spreadsheet or in MATLAB, no problem at all. Or you can use also maps when we have some numbers available. All right, so I'll see you guys. What time it is? What time is 2:30? Or 2:30? So 2 hours for lunch? All right. So I'll see you then at 2:30 here. Any questions from online? So I'll see you guys in a couple of hours.